All right, good morning, everyone. Happy Friday. Hope you're all doing well today. Hopefully you were able to view the section 1.5 video that was posted. Just in case you didn't get a chance, the lecture video is posted, you just scroll down on our homepage of CAT courses, and here's the lecture from section 1.5. It was review exponential and logarithmic functions. And then again, just to mention again, I don't know if anybody's watching these videos, but I enjoy reading the textbook myself. So I started just recording and uploading it. And of course, the videos are a little bit long, but you can always jump around to whatever section you want to watch. And those are optional. So any textbook reading videos are completely optional. One other thing that we could mention is the TAs. At least one of them, I believe, has updated the office hours, maybe both. So today we have office hours. I have office hours right after this class. So feel free to follow me. Last week, a few students followed me to my office and we worked on some trig. Adrian has office hours on Zoom from 3 to 5 p.m. today. So, feel free to join that. And of course, somebody mentioned that this banner was not showing up for them, this little flyer here. So Math 11 tutoring in SSB 320, Monday through Thursday. That's not today, I guess, but every other day, 10 a.m. to 4 p.m. That's a wide range of hours. Some people have mentioned that they can't make it to my office hours. Even if you can't make it to mine, you can go to Adrian or Muzakir. Either any of the three of us will be willing to help you with Math 11 material. And if you somehow can't make it to any of our office hours, they have tutors who have all taken and passed and done well in this course. So visit SSB 320, just go check it out. You can sit there. If you don't need any help, you can just work by yourself and then leave once you're done. But then if you do need help, it's easy to get help. You just say, can somebody help me out? All right. All right, very good. Any questions? So one other thing that we are going to make a change to the syllabus is if you just wanted to mention this, just in case you haven't been told by anybody else, if you feel like you're sick, you might have some sort of symptoms that are possibly COVID symptoms, just stay home, right? Don't come to class. We don't want to be spreading that around. So if you feel sick, just stay home. Even if you have discussion, let's say, we're going to drop more than a normal number of discussion section assignments. In this case, we'll drop 3, right? So if you happen to miss one of them because you felt sick, you wake up not feeling well, just stay in bed, go to sleep or whatever, try to rest. And then that assignment will be dropped and it'll be as if you never missed it, right? Okay, yes? Yeah, so because I heard from another professor told me that if the professor's still sick, they have to Yes, so you should try to get a COVID test. If you feel sick, you should try to get a test as soon as possible and hopefully, it'll come out negative. If you do feel sick and you go get tested and it comes out positive, you need to contact, there's a COVID response team here on campus that you can contact and then they'll kind of give you further instructions. And then you can email your instructors, TAs, and let them know, whatever they tell you, right? So so definitely, at the time, if you feel sick, just don't come to discussion or to lecture. Same thing with the quizzes. 3 quizzes will be dropped. That should be, if you miss one, then don't worry about it. That 0 will be, it'll go away, right? Now, of course, that's only so many. You want to show up to, maybe 2 weeks later or whatever, whenever you feel better. And then 4 homework assignments. So again, that's just if you feel sick and, oh man, there's a homework assignment due tonight, but I feel really bad. My head hurts or something like that. I can't do it. Some homework assignments will be dropped. Now, if you are quarantining in your room, you should still have access to your computer. So, if you feel okay, you can try to get some, get your homework done if you can. That way you don't miss too many assignments, right? The best case scenario would be, you feel good all semester, you do all of your assignments, and then at the end of the semester, 3 of your quizzes, 3 of your discussion sections, and 4 of your lowest homework assignments get dropped. because you missed none, but we still drop your lowest ones, right? That would be the best case scenario, but we're just putting this in place just in case, anybody feels sick and, doesn't feel like coming to discussion or something like that, okay? All right, so just keep that in mind, same thing, if I feel sick, I will just not show up. And we have things in place, somebody either to cover or post the video or depending on what were to happen. All right, so today we are jumping into chapter 2 of our textbook. And this is section 2.2, which is on limits, right? This is a super, super important idea in our class. We're going to talk about it throughout the rest of the class. Let's just talk about a brief definition of a limit. What is a limit? And remember that these notes are posted online. Don't feel like you have to write every single little thing down. But a limit of a function f of x at a number x equals a is the one real number L that the functional values approach as the x values approach a. Okay, so, and then provided such a number exists. So what does that mean? Let's kind of break this down. The limit of a function. So first of all, you have a function and the notation is going to be this. The limit as x approaches a of f of x equals L if it exists. And just one more thing here, I'll put a little notation. That little symbol means L is in the real numbers. Right? You've seen that R, that fancy R, that means it's a real number. Okay, so we say that the limit exists if such a real number L exists. So what do we mean? First of all, there is a function. Okay, well, a function can be in the form of a graph, or it can be given in the form of an equation. So in this case, we're given a graph on the right-hand side, right? Now, we're trying to find a limit of that function. There always has to be some sort of x value, right? So in this case, the x value that is given to us is a, because we're trying to keep things general. So what is a? In this case, we've been given this value here. It's along the x-axis. It's some x value. A is right there. So what we want to know is, as we get closer and closer in the x direction, closer and closer to a, what is the function doing, right? What are the function values approaching, if anything? Okay, so the way that I like to show this sometimes is, as we go, let's say from the left side, because we plug in values of x into our function, and then we get y values out of our function. So what is our function doing? On the left-hand side, it looks like it's approaching this y value, right? In this case, it's L. Now, what about on the right-hand side? What is the function doing on that side? As we go from the right-hand side, I'll do it in red. As we get closer and closer to A, what is the function doing? Well, it's going this way. And this might seem kind of normal. It seems like it's approaching, and you can get super, super close to this. As you get closer and closer to an x value of A, what is the y value doing? What are the function values doing? They look like they're getting closer and closer to some number, and in this case, that number is L. In this case, we say that the limit of the function f of x as x approaches a is L. Okay. So kind of in some nice little words that they put, as x gets closer to a, f of x gets closer to and stays close to L. Okay. Any questions with this idea here? Now we're going to see functions that do a lot of crazy things. And so this one might seem like, well, that's pretty basic. I mean, you're getting closer and closer to A. The function is getting closer and closer to some point. Notice that this function is not even defined at L, right? You see an open circle there. That open circle means the function is not defined there. So f of A is undefined. So the function doesn't actually have to be defined there in order for it to have a limit there. Okay, we're getting really, really close to some value. Maybe we never actually get to that value, but there is a limiting value there. Okay. All right. So we'll start off with a, somewhat basic example here. We look at the function e to the x minus x cubed. There's a couple ways that we could evaluate a limit. The first way that they discuss in the textbook is, if you have a function, you can look at tables. So we want to look at the behavior of the function f of x as x gets closer to 0. Well, there are two ways that we could get closer to 0. We could be negative and increasing towards 0, or we could be positive and decreasing towards 0. So we need to look at both sides of that behavior. Okay, so in our textbook, they actually give a nice little systematic way of finding these limits. And they basically say, take your value a, and then you subtract some small number from it. So this would be 0 minus 0.10, and that's where they get negative 0.1. And then 0 minus a smaller number like 0.01, and that's where we get the next number, and so on. And so then we would plug in these x values into the function. Now, can somebody tell me what value does it seem like these are approaching? We have 0.90, 0.99, 0.9990. Well, it looks like it's getting closer and closer to 1, right? From the table, we can see that. Well, what about from the other side, from the right-hand side? Here we have an a value of 0, plus a tenth, right? This is like a dime, putting a dime on it, or 0 plus a penny, right? Smaller increments. So we're at 0, but then we add some amount, and then we add less and less, and then our value is closer and closer to 0. So 0 plus, there's no equivalent in money, but we have some values here. We plug those x values into the function. We were given the function. And then what value does it seem like f is approaching here? It also seems like it's approaching 1, right? 1.1 decreases to 1.01, decreases to 1.001. It looks like we're getting closer and closer to 1. Now, of course, so we see that it seems like this is equal to 1. We can look at the graph. This is the way I prefer. Sometimes, most of the time, the graph is the easiest way to see it. So that's why we work on graphing. We want to know what graphs look like, exponentials, logarithms, and all those types of graphs. And we can see here, as we get closer and closer in this direction, what is the function doing? It looks like it's approaching a y value of 1. And then same thing in that direction. We're approaching 1. As we get closer and closer to 0, the function gets closer and closer to 1. So we say that the limit as x approaches 0 of f of x is 1. Okay. All right. Sometimes a table is better. Depends on what the graph looks like. Right? You might get a funny looking graph, and then a table could be better. Okay. So two important limit laws. This is theorem 2.1 in our textbook. If we let a be a real number and c be a constant, what is the limit as x approaches a of x? Can somebody tell us what that is? What is the limit as x approaches a of the function x? And we can graph this. That might be, so this one eventually we want to memorize. But for right now, it's okay if we're not sure. We have our x-axis, our y-axis, and our function here, because normally limits are written as the limit as x approaches a of some function f of x and is equal to some real number L if it exists. So the function that is given in this case is f of x equals x. This is the identity function. And you've all seen this one before. This is the simplest line that can be graphed, essentially, with non-zero slope. It's just basically, if you want to call it f of x equals x, or y equals x. So choose any value of a. Let's choose a to be this value here. Okay. If you get closer and closer in terms of x to a, what does y get closer to? What is this value going to be? Right, as we get closer and closer in terms of x to a, what does y get closer to? And since y is equal to x, if x gets closer to a, then y gets closer to a. So the answer here is a. Right? Y is equal to x, that's the function. So we are taking the limit as x approaches a. If x approaches a and y is equal to x, then y must approach a. So we know that that's true on that side. We take a look at the right-hand side. As we approach a on the right-hand side, our function comes down and it approaches this value here, which we know is a. So the answer here is a. So that's one that we want to memorize. One more. Here our function, the limit as x approaches a, usually we have a function here and it's some number L. The function here, f of x, you can see it's replaced by c. C was given to be a constant in that line up above. If c is a constant, then this is a constant function. This has a value c here, and our function is constantly c. Let's suppose that that's, okay, well, close enough. Our function is constantly c. So let's choose an arbitrary value a. As x approaches a on the left-hand side, we're approaching this value here. What is the limit of this function as x approaches a from the left-hand side? What are the function values getting closer and closer to? Any ideas? Any guesses? Just take a guess. I hear some people, I think, saying C. The answer is C, yes, because this function is always C. This function always has a value of C. F of 0 is C, F of 1 is C, F of 2 is C, F of anything is C. So F of A is actually C. The function, as we go, right, we're talking about the height of the function. I can't really point this high, but the height of the function, what are the function values approaching as we get closer and closer to that x value of a? The y values are always c, and they're staying c. As we get closer and closer to a, the function values are approaching or are equal to c. Same behavior happens on the right-hand side as we go from right to left. What are the function values here? And we're talking about these y values of these points as we move further and further towards a. What are the coordinates? We can see that the coordinates of all of these points here, at least the y coordinate, we know is c the entire time. As we get closer and closer to a, they will stay constantly c. So the limit as x approaches a, notice that this one here could have been answered in a sense, what is the constant number c? This is a constant. It's always, it's like if I said, what is the number 5 doing as x approaches 7? Well, the number 5 doesn't change. It's always 5. So the number c is staying constant at c no matter what x is doing. All right. Any questions here? All right, let's continue. So to give more information when a limit does not exist, we introduced the idea of one-sided limits. And so we said that a limit exists if, as you get closer and closer to a in the x direction, the function gets closer and closer to some single value, L. But sometimes functions do different things on each side. So far, we haven't seen an example of that, but we'll see one soon. So a one-sided limit is essentially just looking at the limit from one side. We can look at it from the right. If we're looking at it from the right, then the notation is the limit as x approaches a from the positive side. We all agree that the right side is the positive side and the left side can be called the negative side. So we put this superscript, limit from the left, x as x approaches a from the left, we put that little negative sign kind of like as an exponent or in that same location. of that function f of x. Okay, and so what we mean, let's take a look, and it's already kind of highlighted there. As x approaches some value a from the right-hand side, what is the function doing on the right-hand side? It's approaching, in this case, we can actually write it out. The limit as x approaches, let's see, in this case, it is 1 from the right-hand side of this function f of x. This is equal to 2. Let's check our understanding here. The limit as x approaches, let's say 2, or from the left, yeah, 2 from the left of this function. Can somebody tell me what this is equal to? The limit as x approaches 2 from the left. What would that be equal to? Yes? Huh? Not 1, no. The limit as x approaches 2. I changed it from what the yes, if x approaches 2, what does the function approach? Yes? 5. Yes, because as we get closer and closer to 2, so we're going in this direction, what is this function doing? This function is approaching this value here, which looks to be 5. Okay, does everybody see that? So this is a limit from the left. We're coming in from the left side of 2. And then what is the function doing on that side? It is increasing towards 5. Okay. Is that okay for everyone? All right, very good. All right. Yeah, I kind of switched it up there from what was on there. Okay. So when does a double-sided or two-sided limit exist? If the positive and negative sided limits both exist, are the same finite value, then we say that the two-sided limit exists and it is equal to either one of those two. Okay, so let's take a look here. We'll kind of break it down. We've already seen this graph. We know that the two-sided limit exists, but how do we show that it exists? We need to find the left-handed limit and the right-handed limit. So the limit as x approaches a from the left-hand side. So from the left-hand side, what is my function doing? It is approaching L, right? So we say that the limit from the left side is L. What is the limit from the right side? Well, from the right side, the limit as x approaches a from the right, well, from the right side, as we get closer and closer to a, it looks like we're getting to a y value of L as well. So the limit from the right-hand side is L. When these two are equal to each other, as they are in this case, then we say that the double-sided limit, the limit as x approaches a of f of x exists and is equal to L. Okay, so basically the function has to be going towards the same value from both sides. We'll see examples of where this does not happen shortly. Okay. All right, and so let's try to say the limit for when we mean a double-sided limit, you know, in general, both the left and the right. And then of course, we'll say the limit as x approaches a from the left, if we mean a left-sided limit, or the limit as x approaches a from the right when we mean a right-sided limit. Okay, so if I ever just say the limit of this function is this, I'm talking about the double-sided limit. All right, so let's take a look at, showed her head already. Let's take a look at the one-sided limit here. And maybe somebody can help me here with part A. What is the limit of this function f of x as x approaches -2 from the left? So along the x-axis, we're doing this. What is my function approaching? It looks like it's 3. Yes, very good. So the limit from the left side is 3. What's the limit from the right side? Let me use a different color here. The limit from the right side, as we approach -2 from the right side, What function value is my function approaching? 3 again. Yeah, that's somewhat typical behavior of a function sometimes. So then we can say, because of this, we can say that the limit as x approaches -2, the double-sided limit, exists and is equal to 3. Okay? Because the first two exist, the third one must exist. The double-sided limit must exist and must be the same value, 3. Okay? The part C, before I highlight it here, can anybody tell us what is the answer to part C? Say again? 4? Yes, because this is a right-sided limit. From the right side, as we approach 1, what is my function value approaching? It is approaching a height, basically, of 4. So the answer there is 4. What about from the left-hand side? It looks like it's -3. All right, very good. So as we approach 1 from the from the left-hand side, excuse me, our function is approaching a height or a y value of -3. So then what does this tell us about the two-sided limit? It doesn't exist, right? We said that the left-handed limit and the right-handed limit have to be equal in order for the two-sided limit to exist. And so if they are not equal, like in this case, then the limit does not exist, right? And you all remember that from, have you seen the movie Mean Girls? Yeah. Check out the limit. Actually, I wanted to look it up yesterday because what was that limit that they were talking about in that class? You actually can do that problem now, and using a table would be the best, actually, the best way to do that one. Actually, the graph would work as well. Okay, so in this case, we would say that the limit as x approaches 1, this is the double-sided limit because I'm not putting a superscript of a negative or a positive of this function. And we say in this case, does not exist. We usually write just DNE, capital DNE, or does not exist. Okay, this is the notation that we should use here. You don't have to put equals DNE because it does not equal a certain value. It just does not exist. Okay? All right, because we said in the previous slide, we were talking about the existence of limits. The double-sided limit, you can see in that box, in the white box with the red border, the double-sided limit exists and is equal to L if and only if the two one-sided limits exist and are also equal to L. Okay, okay, any questions there? All right, very good. So, okay, sometimes a function, so we've seen two cases. Let me scroll back really quick here. The two cases are when we're approaching -2, sometimes both sides approach the same value. In this case, 3. Sometimes a function, this is a piecewise function, you've seen these in pre-calculus, they approach 2 different values. If you approach 2 different values, those values are not the same, the limit does not exist. But what other options are there, right? The other option is a function that shoots off to either positive or negative infinity. Okay? In that case, we technically say that the limit does not exist, or we're not saying that the limit exists, but we have a notation to give a little bit of detail as to what the function is doing near that value of a. Okay? So let's go ahead and kind of talk about this here, break this down a little bit. Consider the function f of x equals 1 over x minus a to the n. Okay, and a couple examples that we're going to look at here. If you let x be 0, an example of this would be 1 over x. I believe you have seen this function before. And then another function, f of x equals 1 over x squared. If we have time, we'll talk about these in a little more detail. But a function like this shoots off to infinity. So we could have this behavior as we see in this graph here. Let's start with the left-hand sided graph. What would the limit as x approaches a be from the left-hand side? Well, you see it goes down to negative infinity. Right, just keeps going lower and lower. If you looked at a table and plugged in numbers that were closer and closer to A, you would get output values that are more and more negative. Whenever this occurs, we say that the limit is negative infinity. Okay? Similarly, on the right-hand side, the behavior as x approaches A from the right is to shoot off to positive infinity. So in this case, the right-handed limit would be positive infinity. For the odd values of n, can somebody tell us what would be the double-sided limit? What would the limit be of this function as x approaches A? Does not exist because the left and the right-handed limits, they don't match up. So that one definitely will say does not exist. Now, if you read the textbook and you look at the intricacies of this thing, we technically say that this limit here, this positive infinity, technically is not a limit as we have defined the limits. Because is positive infinity, is this equal to some number L, which is a real number? No, infinity is not a number. So it technically does not fit the definition of a limit, right? So whenever we have an infinite limit, I'm going to erase that here, but whenever we have an infinite limit, let's go ahead and say that the limit is either positive or negative infinity. But technically speaking, it does not fit the definition of a real valued limit, let's say. Okay. So just a little intricate thing there. Now, what about when we have even values of that exponent n? The even value knocks out any negatives whenever you square or raise a negative to the fourth power, then both sided limits would be equal to positive infinity. So in this case, we can say the limit as x approaches A of f of x is equal to positive infinity. Any questions? So, yeah, something that I thought was kind of cool was just, what do we call that? What do we call that red vertical line there? You've seen those before. Anybody remember what those are? An asymptote. Yeah, this is a vertical asymptote. So I just thought it was kind of cool when you get into this class, even in pre-calculus, I believe in my pre-calculus class, you can now define what a vertical asymptote is. I mean, I could have asked you, what is a vertical asymptote? Can you tell me what that is? You would say, well, that's like where a function is getting closer to some value and then goes either to positive infinity or negative infinity, something along those lines. So we can now define a vertical asymptote in the language of limits. Okay, so here's our definition for vertical asymptote. If f of x is a function and one of the following conditions hold, then we say that the line x equals a is a vertical asymptote of that function f. What are these conditions that need to hold? Well, if f has a left-sided limit of either positive or negative infinity, right? As you get closer and closer to some value a, if f goes to negative infinity or positive infinity, then there must be a vertical asymptote there at x equals a. Okay, so a very precise definition for a vertical asymptote. Same thing from the right-hand side. The limit as x approaches a from the right-hand side of this function, if it is positive or negative infinity, then we say that there's a vertical asymptote there. Okay, you can graph it. There must be a vertical asymptote there. Okay, the third condition. Why is the third condition redundant? Can anybody tell us? We really don't even need this third condition here. Why is it redundant? Can anybody tell us that? It was in the textbook, so I put it in there. Sure. Yeah. maybe. The third condition is redundant because if the third condition holds, then the first two must hold, right? If you have a two-sided limit of positive or negative infinity, then of course the left-handed limit is already positive or negative infinity. Same thing with the right-handed limit, right? So that's why it's redundant, because if the third one holds, then you don't really have to list that third one because the first two are already satisfied. We will come back to these examples here. So let's go ahead and take a look at these examples. I think we will have time to come back to the other ones, but let's just take a look at these and maybe somebody can help us here. The limit as x approaches -3 from the left-hand side, and let's assume this function here graphed is h of x. What is the limit of this function as x approaches -3 from the left-hand side? Yep. Would it be negative infinity? What do we think? As you approach -3, the function approaches negative infinity. That is correct. Yep. Very good. What about the next one? From the right-hand side. Right? In the yellow shirt, you give a shot at it? Yes. It would be positive infinity. Yes, very good. Just want to make sure everybody's, that we see this, right? Because this is something, we just kind of got to look at these graphs and we should be able to see it and, understand what the limit is. In the gray shirt there, can you answer the next one for us? What is your name? Gabriel. Can you help us out here with the next one? The limit as x approaches 2 from the left. The limit as x approaches 2 from the left-hand side. So as we get closer and closer to 2, what is our function doing? From the left-hand side? From the left-hand side, our function is going down. So the limit would be negative infinity. All right, very good. And then the last one, yes? It would be positive infinity. Very good. All right, so for either one of these two limits, the limit as x approaches, let's say 2 of this function, h of x, we would say in this case, does not exist. Okay, hopefully that's not too bad. Yeah, we're going to come back to this idea quite a bit throughout this class. All right, so yeah, really quick, we have another couple minutes let's do this one before we go back. So let's just write down a couple of things here. The limit as x approaches 1 from the left, the limit as x approaches 1 from the right. We want to know what f of 1 is and what the limit as x approaches 1 of f of x is. And let me switch these two questions just to okay, these are all questions that we should be able to answer now. And then while you're thinking about that, the limit as x approaches -2 from the left, the limit as x approaches -2 from the right, And then while you're thinking about that, the limit as x approaches 3 from the left, from the right, from both sides, and f of 3. Oops. All right, let's get some answers. They're in the back there with the orange pencil. Yeah. Yes. What do you think of the limit as x approaches 1 from the left? It is 6 from the left. All right, very good. Nice. And what was your name? Say again? Araceli. All right, thank you. And then in the front, you were volunteering here. What about the next one? It is 3. Yeah. All right, our function is going towards 3. Very good. Here in the front, yeah. The next one. It doesn't exist, right? Because the left-handed limit is 6, the right-handed limit is 3. Those are not the same, and the double-sided limit cannot exist. So if anything, I should actually even erase these equal signs here and just put D and E. Okay, what is f of 1? Here in the front, f of 1. What is f of 1? There is an open circle there. So that is, it would be 6. Very good. Yeah, so the function can be defined. It might have even been defined like if that circle, if both of those were open circles and then the dot was even higher, it could have been 8 or something else. The limit does not necessarily have to equal the function value, right? In this case, it did equal one side of the limit, one of those two-sided limits. It equaled the limit from the left-hand side. So 6. All right, very good. All right, next one. Any volunteers? Yes? As x approaches -2 from the left-hand side is 3. Very good. All right, what about the right-handed limit? Yep, it is 3 as well. So then in this case, when the two single-sided limits are equal, the double-sided limit must exist and must be equal to 3 as well. What about f of -2? It doesn't exist. For function values, in this case, the terminology here, we would say f of -2 is undefined. Yeah, that's the terminology we normally use in a pre-calculus class. Okay, very good. And then since we're running out of time here, just shout out what's f of what are the limits for the last one? -infinity. Very good. Then the right-handed limit is also -infinity. Then this must be -infinity. What is f of 3? It is undefined. Very good. Yeah, there is no function value, right? It's going to infinity. The function is not actually defined there. So we say f of 3 is undefined. All right, very good. We still have one more example to cover. We got 5 minutes left. We'll skip this one here. This one it's in the textbook. Let's take a look at one more example here. And this example is basically going off of this infinite limit idea here. One thing that you need to see, well, is this example. All right, let's take a look at it. So this function is following the form 1 over x minus a raised to the n. Okay, in this case, I chose a to be 0. That means this function will be shifted left or right 0 units. So it's centered at the y-axis. And then it's raised to the first power. So it's an odd exponent, which means that the end behavior should be one rises and the other falls. Okay. All right. So to write this more simply here, I just wrote it in this form just to show that it was of the form that we were talking of on the previous slide. But this is just 1 over x. So if we wanted to find, well, first of all, can somebody tell us where is an interesting limit going to come up? Where are we going to have an issue with this problem or with this function? At what x value? Which one? 0, yes, because 0, the function is undefined there, right? F of 0 is not defined. So let's go ahead and take a look at the limit as x approaches 0 from the left of this function of 1 over x. The limit as x approaches 0 from the right of 1 over x. The limit as x approaches 0 of 1 over x. And then we can look at f of 0. We just said this is actually undefined, so this is undefined. So how do we look at the limit from the left-hand side? There's two ways. You can graph it or you can make a table. Let's make a table here. Let's take a look at, just for the exercise here, x and f of x, or y values if you prefer that. What values could we plug in here on the left side? Let's give some ideas for y values that we could plug in from the left-hand side. Say I want to construct a table. What y values should I plug in? I'm sorry, what x values should I plug in? We always plug in x, right? Not y. -1. Okay, very good. So we're going to plug in -1, and then we're going to choose values getting closer and closer to 0. Right? So -1. We could try -0.5, right? Half of that. And then let's try half of that. -0.25. -0.125. And then what is half of that? That would be -0.06. What is half of 0.625? Right? If we split that in half. So let's plug these into the function. What is f of -1? F of -1 is 1 over -1. This is -1. Okay. We want to see the trend of these y values. What are these y values going to do? Does anybody have any idea? I mean, we've already shown the graph, a rough idea of the graph. Closer to 0, not past 0. Any other ideas? Negative infinity. Anything else? Let's take a look. So notice that we're plugging in smaller and smaller numbers, right? You agree that these x values are smaller and smaller. Okay, so this is going to be a trend that we're going to see a lot in this class. F of -0.5, this is 1 over, and if you write -0.5 as a fraction, this is -1/2, right? And so you have 1 times a -2 over 1, which is -2, right? I flip the bottom and multiply. We can punch this into our calculator. We would get -2. Notice the number is becoming more negative, at least so far. So we're looking like maybe the negative infinity idea is correct. F of -0.25. You all know that -0.25 is -1/4. So this is 1 times a -4 over 1. This is -4. F of -0.125. Now, there's a calculator right here, so I can use this. This is now my fractional skills here are failing me, so I'll just punch it into the calculator. 1 divided by -0.125. This is equal to, of course, -8. We're having each of the x values. So here we get -8, and then the next one would give us -16. As we put numbers that are smaller and smaller, this limit would be negative infinity, right? We need to choose values that are even smaller, and the function would grow even greater. So you can do this on your own. For the other sides, you would get positive infinity for the other side. The main thing that I wanted to show here is if you have 1 over x, and you get numbers that are smaller and smaller in the denominator, the function actually grows larger and larger. Okay. So the homework assignment is already posted. It'll open up in a couple minutes, in 10 minutes. Have a good weekend. If you have any questions, come on by. Say again? Yes.
So